Welcome to Lesson 32, Simplifying and Evaluating Expressions with Integer and Zero Exponents. We're going to start off with a little exploration here and just fill in the values of the following exponents. So the first one are powers of 2. 2 to the fourth power would be 2 times 2, which is 4, times 2, which is 8, times another 2, which is 16. So go ahead and write in 16. And 2 to the third power, would be 2 times 2, which is 4, times 2, which is 8. 2 times 2 would be 4, or 2 squared. 2 to the first power is just 2. Anything to the first power is itself. 2 to the 0 power, you'll find out, well, you already probably know, but also in your notes below this is the zero exponent property, which is that for every non-zero number that is raised to the 0 power, it equals 1. Okay, now we're just going to skip over to powers of 3 for a moment and fill these in as well. So we have 3 to the fourth power. 3 times 3 is 9, times 3 is 27, times 3 is 81. My 8 turned out funny there. 3 to the third power is 3 times 3 is 9, times 3 is 27. 3 squared, 3 times 3 is 9. 3 to the first power is itself 3. And 3 to the 0 power, we know, is 1. Anything to the 0 power equals 1. So I want you to take a moment here and look for some patterns with me. So a pattern for the powers of 2 is that 16 divided by 2 is 8. 8 divided by 2 is 4. 4 divided by 2 is 2. And 2 divided by 2 is 1. So if we follow this pattern here, our exponents are going down each time by 1. So 4, 3, 2, 1, 0. But each time the value is being divided by 2. So if we follow that pattern, here for 2 to the negative 1 power, we would take the previous value, which is 1, and divide it by 2, which would be 1/2. And then again, 2 to the negative 2 power, we would take 1/2 and divide that by 2. And 1/2 divided by 2 is 1/4. If we cut 1/2 in half, it's 1/4. So I want you to notice this, that 1/2 is actually 1 over 2 to the first power, and 1/4 is actually 1 over 2 to the second power. Okay, now moving on to the powers of 3, we're going to see if it follows a similar pattern. So between 81 and 27, we divide by 3. Between 27 to 9, we divide by 3. 27 divided by 3 is 9. And again, we're going to keep dividing by 3 to get these values. So if we follow the same pattern, we would take 1 and divide it by 3. And then we would take 1/3 and divide it by 3. So if we take thirds and divide it into 3 pieces, we'd have 1/9. Now I want you to notice here that this is 1 over 3 to the first power and 1 over 3 squared. So there's a connection here between this and this on both of these examples. So if you look down on your notes, there's a property that describes this pattern that we just discovered. So for every non-zero number x, so that means any number that's not x, it could be positive or negative, if it's held to a negative exponent, oh, I forgot the negative sign when I typed this up here. So x to the negative n should be 1 over x to the n. So you need to add in here an exponent of n. So as you can see, the negative disappears on the exponent when you move it to the bottom of the fraction. And the same is true of the reverse. So if we have x to the n power, we can move it to the bottom of a fraction and call it x to the negative n power. So it works both ways. And then again, the zero exponent property is here for you, just to remember in your notes that for anything held to a zero exponent, it equals 1, no matter what the base number is. And just a couple of reminders here. The product property of exponents is when exponents of the powers with the same base are added. So an example of that would be if we have 2 to the third power times 2 to the fifth power, that's going to equal 2 to the 3 plus 5 power, which is 8th power. And an algebraic expression is not considered simplified if it contains negative or zero exponents. So if you have a negative exponent, you need to move it to the top or bottom of the fraction, whatever is the reverse of where it is to begin with, to get rid of that negative exponent. So let's look at a couple of examples here, because I'm sure you're thoroughly confused by my description. So if we have x to the negative 9 power, then we would turn this into a fraction, and we would put x to the 9th power on the bottom of the fraction, but we still need something on the top of our fraction, so we just use a 1 as our numerator. And that is now simplified. Our next example, d to the negative 2 power over c to the 3rd power. Now we don't know what these variables are, so c to the 3rd power is as simplified as we can make it, but d to the negative 2nd power is not simplified because it has a negative exponent. So we need to take this exponent with its base and move it to the opposite side of the fraction. So now on the bottom we're going to have c to the 3rd power because that didn't go anywhere. But we also are going to have d to the 2nd power, and the negative disappears from our exponent. And on the top we're just left with 1. Nothing else is left up there. So that's now simplified as much as possible. Our next example is 1 over d to the negative 5th power. And now our negative exponent is in the numerator, or the denominator, of our fraction. So all we need to do is now move it to the top instead of the bottom. So now we're going to have d to the 5th, and the negative disappears, over 1. And we don't need that 1 on the bottom because anything divided by 1 is itself. So it's just d to the 5th power. And now that is simplified. Moving on to a couple more examples. Now we're actually going to solve using numbers. Just a caution in this box is it's a common mistake to incorrectly replace a number to the 0 exponent with 0 because we know a number times 0 is 0, but a number to the 0 exponent is actually 1, and we need to remember that. So we're going to plug in some numbers here. First we have negative 7, because negative 7 is a, to the 0 power, and then b is negative 4. Notice how I'm using parentheses around these numbers because they include negatives, to the 2nd power. So negative 7 to the 0 power, according to the 0 exponent rule, is 1. And negative 4 to the 2nd power, negative 4 times negative 4 would be positive 16. And 16 times 1 is 16. The next example, we're going to use the same values for our variables. Start off with an 8 times b, which is negative 4 to the negative 2nd power, times b again, negative 4 to the 1st power. Okay, now, first of all, we have to move this negative 4 to the negative 2nd power to the bottom of this fraction. So we make this a fraction and move it to the bottom. So now it's negative 4 to the 2nd power on the bottom. So we have 8 over negative 4 times negative 4, which is 16, times negative 4 to the 1st power, which is negative 4, over 1. So if we cross cancel here, 4 goes into 4 one time, but this is a negative because it's a negative 4. 4 goes into 16 4 times. and we'd have 8 times negative 1, which is negative 8 over 4, and negative 8 divided by 4 is negative 2. Keep moving on. We talked about the product property in the reminders on the first page of your notes, and now we're going to introduce the quotient property, which is the opposite of the product property. So an example of this is when you divide two expressions with the same base, you subtract their exponents instead of adding them. Since division is the opposite of multiplication, we subtract instead of adding. So an example of this might be 5 to the 4th power over 5 to the 2nd power would be 5 to the 4th power minus 2nd, so 5 to the 2nd power, which equals 25. Now if we use variables to write this, an example might be x to the 7th power over x to the 3rd power would be x to the 7 minus 3rd power, which equals x to the 4th power. My pen isn't working. So let's try a couple examples here. X to the 9th power over x to the 6th power, we're just going to subtract 9 minus 6 to get x to the 3rd power. Next example, we have x to the 9th power over x to the negative 6th power. And we can either move this first to the top, so we'd have x to the 9th power times x to the 6th power, which would be x to the 15th power. That would be the product property rule. Or you can use the product or the quotient property rule instead and do 9 minus negative 6, which would actually be 9 plus 6, which equals x to the 15th power. So you get the same answer either way. Okay, and this last example looks scary, but all we need to do here is find the x's that are the same, which we have x and x to the negative 4. So that would be x to the 1st power divided by x to the negative 4th power, so minus negative 4. And then we have y's. So we have y to the negative 6th power minus negative 5 because we're dividing. And then z to the negative 3rd power divided by z. So z to the negative 3rd power minus 1, because it's z, just z is to the 1st power. So 1 minus negative 4 would be 1 plus 4, which is x to the 5th power. And the y's would be negative 6 plus 5, which is negative 1. And then the z's would be negative 3 minus 1, which is negative 4. And then we need to move these to the bottom of our fraction. So I'm out of room. I'm going to have to write this over here. We'd have x to the 5th power over y to the 1st power, which is just y, and z to the 4th power. So that's our final answer there. Okay, last example. A kilometer is 10 to the 3rd power meters. How many times larger is a kilometer than a millimeter? So I wrote this out kind of on a scale here. I have, not 10, I should have 1 meter is equal to 10 to the 3rd, 10 to the 3rd meters is equal to 1 kilometer. And on the other end of the spectrum, 10 to the negative 3rd power is equal to 1 millimeter. So that's 1 millimeter for every, 1 meter for every 1,000 millimeters. I can't talk today. And then over here is 1,000 meters, for 1 kilometer. So if we look at how much is in between these, there are 6 spaces in between them, so it's 10 to the 6th power times larger. 10 to the 6th power is also 1 million times larger, because the question asked us to put this in exponential and standard form. And that's our lesson. Thanks for listening and taking notes.